Welcome back to The Explainer. Today we're diving into a real measurement mystery. We're going to play the role of scientific detectives and solve a microscopic puzzle using some foundational and, honestly, pretty cool chemistry lab techniques. So get ready to focus in, because we're about to learn exactly how to take ordinary, everyday objects and use science to reveal secrets that are literally invisible to the naked eye.
Okay, so picture this. You've got a completely normal, seemingly ordinary sheet of aluminum foil. You probably have a roll of it sitting in your kitchen drawer right now. But here is the core problem we're tackling today. How do you measure a thickness you can barely even see? I mean, we have everyday tools, sure, but this foil is way too thin for a standard metric ruler to give us any kind of accurate reading. The tiny millimeter markings on a regular ruler, they just do not go small enough to capture the true thickness of this sheet. It's a really fantastic physical puzzle, just waiting for us to solve it.
Section 1. Chemistry Lab Survival Guide. Now, before we can actually start solving our mystery, we first need to gather our scientific armor, right? You can't just stroll into a laboratory and start measuring things. Safety is the absolute priority here. First off, you always have to follow the specific instructions from your instructor and your lab manual. You need to be wearing the appropriate PPE, personal protective equipment, at all times. We're talking high-impact safety goggles to shield your eyes from any unexpected splashes. You also need to keep that workspace totally clean and organized. A clean bench isn't just about making things look nice, it literally prevents unintended cross-contamination that could completely ruin your data or, worse, cause a dangerous reaction. And if anything does happen, you report it to your instructor immediately. Oh, and absolutely no eating, drinking, or chewing gum in the lab. Keep the snacks outside, guys. You definitely don't want to accidentally ingest your chemistry experiment.
And when you first walk into that space, your very first task as a scientist is to build a mental map of the room. You absolutely must locate the eye wash station, the safety shower, the fire extinguisher, and the first aid kit. Why do this right away? Well, because in the rare event of an emergency, panic sets in fast, and you're not going to have time to go wandering around looking for help. It's a critical procedure to remember. If you ever get a chemical in your eyes, you have to get to that eye wash station immediately and continuously flush your eyes while calling out for your teacher. Knowing exactly where these life-saving stations are before you even touch a piece of equipment, totally non-negotiable.
Moving on to technique. You know that slight curve at the surface of a liquid inside a graduated cylinder? That little dip is called the meniscus. When you're using laboratory glassware, whether it's beakers, Erlenmeyer flasks, burettes, whatever, you have to learn to read that meniscus perfectly at eye level. If you look down at it from above or kind of gaze up at it from below, the glass distorts the image. It'll actually give you a false estimation of the volume. So getting your eyes perfectly level with that bottom curve is what ensures you're gathering highly precise measurements. It's basically the foundation of good chemistry.
All right, this brings us to our secret weapon for today, the analytical balance. It's a highly sensitive instrument used for precisely weighing chemicals, and it is going to be the absolute star of the show for our foil experiment. Just to give you an idea of why this thing is so special, it's not like your standard bathroom scale. Actually, it's pretty much the exact opposite. It's usually enclosed in glass because even the slightest air currents in the room, like just someone walking by, can alter the reading. It measures mass down to fractions of a single milligram. Just for context, in a well-equipped lab, you'd also be using things like hot plates to heat solutions or centrifuges to separate them. But for our impossibly thin foil, this extreme sensitivity is exactly what we need.
One final survival rule before we start getting our hands dirty. Always record your observations and data in your lab notebook in ink. Your documentation has to be a permanent record. In real science, mistakes aren't just erased and swept under the rug. If you mess up, you just cross it out with a single line. That way, you and any other researchers can trace your entire thought process and see exactly where things went right or wrong. Be super thorough. Include the title, the purpose, your materials, the procedure, and of course, your results. And hey, when you're all done, make sure you properly dispose of any chemical waste and wipe down that bench so it's a perfect blank slate for the next scientist.
Section 2. The Foil Thickness Experiment.
Okay, our scientific armor is on and we've reviewed the basics. Let's get to the main event. We're going to apply these precise lab skills to figure out the exact thickness of two completely different brands of aluminum foil. Here's what we need for the mission. Our two brands of foil, that highly sensitive analytical balance we just talked about, a metric ruler, and some scissors. And as strict lab protocol dictates, you must have those safety goggles and a thick lab apron on the whole time.
Quick reality check before we start snipping. Scissors are sharp. I know, it sounds ridiculously basic, but please use them with care so you don't end up cutting yourself or someone standing next to you. In a busy, active lab with people moving all around, keeping these incredibly simple physical precautions top of mind is exactly what prevents silly, everyday accidents from completely halting an experiment.
So here's our game plan. Our procedure is basically an action sequence of 3 super deliberate, straightforward steps to gather our raw data. Step 1. You grab the scissors and your metric ruler, carefully cut a perfect rectangle from the first brand of foil, and calculate its area. Just length times width. Step 2. Take that little foil rectangle, carefully place it inside the analytical balance, and find its exact mass down to the milligram. These 2 metrics, the area and the mass, are our crucial pieces of physical evidence. And step 3, just repeat that whole process with the second brand of foil. Boom, data collected.
Section 3. Crunching the density data.
All right, here is where it gets really exciting. We've got our raw numbers. We know the area from the ruler, and we know the mass from the balance. But how on earth does that give us a microscopic thickness? Well, the answer lies entirely in this one specific number, 2.699. That is 2.699 grams per cubic centimeter. It is the constant density of aluminum. Because it's a physical constant, it means that no matter the size, the shape, or the extreme thinness of a pure piece of aluminum, its density is always going to be exactly that number. This single figure is the magic key to unlocking our whole mystery.
Basically, density hacks the system for us. It's a brilliant indirect measurement technique. So let's break it down. Because we know the constant density of aluminum and we just found our foil's exact mass, we can take that mass and just divide it by the density. Mathematically, that immediately gives us the foil's true total volume. Now imagine that newly calculated volume as a really flat 3D box. We already know the length and the width, the surface area, because we measured those edges with our ruler in step 1. So if we take the total volume of that 3D box and divide it by the surface area, what's perfectly left over is our hidden thickness. We literally just used algebra to find a dimension we couldn't even physically see. How cool is that?
Of course, our final analysis means we need to map out all these calculations in a standardized data table. We're going to take our newly calculated thickness and report it across 3 different units, centimeters, meters, and micrometers, for both brand 1 and brand 2. Now, contextualizing data like this is absolutely vital in science. Why? Because it helps us find the most readable number. Honestly, a number with a half dozen zeros after the decimal point is just a nightmare to read and communicate. So converting it into a logical scale ensures your data is actually useful and makes sense to other scientists.
And once that table is completely filled in, the mystery is solved. You can finally close the case and answer the ultimate question: which brand is the thickest? You've got the undeniable mathematical proof staring right back at you, allowing you to directly compare the manufacturing standards of these 2 foils. It is a huge triumph for indirect math over trying to use a microscopic ruler.
But before you completely pack up, look back at those columns of data. You've got one last analytical question to chew on. Which unit is actually the most appropriate to use here? You really got to think about your reasoning. I mean, you wouldn't measure the driving distance between New York and LA in inches, right? So you have to decide why a tiny unit, like micrometers, might make way more logical sense than meters or even centimeters for describing something so impossibly thin.
And that brings us to a fantastic wrap-up for this explainer. By mastering just a handful of basic safety protocols, wielding an analytical balance the right way, and creatively applying a simple constant like density, we solved a microscopic mystery from scratch. Which leaves me with one final thought for you to chew on. If a basic concept like density can indirectly reveal the microscopic thickness of ordinary everyday kitchen foil, what other invisible measurements are hiding in plain sight right now in your very own home? Keep exploring, keep questioning, and I'll see you on the next explainer.